In this video, I will be modeling a project that I have previously worked on in SAM. I'll show you how to fit a residential home in the State College area with an appropriate solar array. The goal of this client was to maximize the solar potential of their roof in order to completely offset the home's energy usage, which was about 10,000 kilowatt hours annually. This home has about 500 square feet of usable roof space, so we will need to take that into account when sizing our solar array. The first step is to open the System Advisor Model program. So when you open it, you'll see an option to either start a new project or open a previous project file. For this instance, we're going to start a new project, but if you were continually working on a solar project, you want to open the existing project file. The next step is to choose what type of solar array you will be modeling. In this case, we are going to do a small-scale residential array, so we're going to do the photovoltaic detailed and then the residential distributed, and then we're just going to click OK. So the next step is to choose a location and resource. We're going to assume that this house is in State College, so we can search an area in the Files Library section, and SAM already contains a database of weather data from certain regions. And in our case, Penn State has its own SurfRad data collection site, which provides very accurate and consistent weather data. So we can type in Penn State, or even State College will work, into the search bar, and we're going to choose the Penn State State College option, and all of the weather data from the file will be immediately imported up here. So one thing to note in the case of weather data, the surrounding region is specific enough. For example, you can choose the State College data for Ferguson Township, but most local airports actually have their own weather data records and should be available on SAM. The next step is selecting a module that has to do with the specific price point of the client and how much they value price over efficiency and aesthetics. Usually you present the client with two different options: one panel with less power that costs less overall, and another module option with more power that is more expensive and allows them to allow them to choose whether they want to lower the cost or maximize the power. The manufacturers typically produce two different levels of the same module design in order to give consumers a higher and lower end purchasing option. This is the same as buying a more expensive washer and dryer that will wash and dry your clothes much faster than the lower end, cheaper model. But some consumers will still choose the lower end model just due to the price point. For this screencast, we're going to choose the SunPower X20 CAC because it is a popular panel used by solar companies in the State College area. This is the module with the maximum amount of power output, since we are assuming this particular homeowner wants as much power as possible. So the SunPower panel that we just picked comes with a built-in microinverter, so it does not require one giant inverter connecting them all. Microinverters allow the entire array system to stay operational even if one panel is shaded and not able to produce power. Without individual microinverters, the entire array system would shut down if one panel was shaded. Think of this as an open series circuit, and microinverters wire the array in a parallel circuit format. Since the inverter already is included with the panel, we're going to select the same microinverter model, making sure to choose the same voltage as the panel. This voltage refers to the voltage output and efficiency of the panel. If we choose a panel without the built-in microinverter, you would just have to choose an efficient inverter that works with the module you choose. The next step is coming up with a system design. This is a more involved step with multiple aspects to keep track of. This is the section where we determine the array size and the area it will take up. For this project, we are given a specific roof size, which is 400 square feet, which is around 37 meters squared. Note that we must convert from square feet to square meters because American construction design is typically measured in square footage, and SAM shows a total module area in meters squared. Specifying an array size in kilowatt DC becomes a guess and check procedure. You can start at a reasonable number, let's say 4 kilowatt DC, and then check the total module area under the estimate of overall land usage section. And after a few tries, we can settle in on an 8 kilowatt DC array. We want to stay just under 400 square feet in order to leave room for the overhang section of the roof, which we can't have panels on due to weight loads. Tracking and orientation are also an important part of every solar array. Now, for a residential array, the panels will be fit at the angle of the roof, so you can select the fixed option under the tracking and orientation and enter in the tilt of the roof. In this case, it's 27 degrees, and the azimuth is 180 since the panel is stationary. Remember, the azimuth is the exposure to the horizon. It is 180 degrees from the sun rising in the east and setting in the west every day. The next step is to determine shading. We will assume that this home is set in a treeless lot with neighboring homes not shading the roof or the panels on our home. This is typical for new commercial construction homes, which are typically built in empty lots in pre-constructed neighborhoods where the lots are cleared of trees and the neighboring homes are the same height. Due to this, there will be no outside shading. If there was shading, it could be modeled using the SketchUp program, and the data could be imported to SAM through the use of the Skeleton plugin. The next thing we have to do is to record the losses of the system. Since the panels we have chose have built-in microinverters, we must account for these losses differently. In the default DC losses subsection in the DC losses main section, click the microinverter button and SAM will update the losses automatically to account for built-in microinverters. Next is to determine the electricity rates in the area that you are installing the panels. To model the energy savings as accurately as possible in the final output, look under the OpenEI US Utility Rate Database section and click the Search for Rates button. This will redirect you to a pop-up window where you can enter State College zip code 16801 and select Residential Only in the drop-down arrow menu directly across from it. For this particular area, West Penn Power Company is the only electricity provider in the region. The last step is to choose a domestic service that is up to date. Lastly, click the Download and Apply Utility Rate button to update the data in the model. Note that this option is to provide you with the average idea of power savings in the area and might not be completely accurate to the savings the homeowner will get. The final step is to simulate our module array. You can click the Simulate button and SAM will output a series of charts and graphs for you to analyze. The first thing you see is a chart explaining different number outputs. Annual energy output by the panels is given in kilowatt hours, and that is the rating of the PV system accounting for any losses and shading data. This number is what the array will output in its first years of operation, since annual energy production will decrease slightly each year as the panels age. This trend can be seen in the annual energy production graph, giving an estimated 1,000 kilowatt hour loss over 25 years. The electricity bill estimate is in the negatives now. This means the resident can negotiate with the power company to sell some of the power they are generating back to the grid. The after-tax cash flow system lifetime graph shows a large cost in the first year, which is the initial cost of the system and installation. But each year after the first is in the negatives as the homeowner saves on electricity bills and even earns some energy rebates on electricity sold back to the grid if the house overproduces electricity that it doesn't use. The last thing to do is print out a spec sheet to hand to the client. It is professional to be able to hand the client a clean, easy-to-read document explaining the technical and basic elements of the solar project you are proposing to install on their building. To print this spec sheet, click on the down arrow by the name of the project and click Create Report. This will print a PDF sheet summarizing the output chart explained previously. The last thing you have to do is present your results to the client. Give the SAM report you just made to the client or professor you are performing this analysis for, and you've done your job. Congratulations, you're a solar expert now.